Good afternoon, this is Schweitzer, and this is a video that's primarily focused on angular acceleration. But what we'll do here is we're going to do a little bit of practice with some of our old concepts. So we have angular velocity, and we're going to be introducing the new concept of angular acceleration, which looks like that little guy. So this is the angular velocity, and this is the acceleration. But either way, let's start out with a couple practice problems. You should be pausing and trying some of these out. So it says through what angle, or theta, must the wheel shown at the right turn in order to the right to turn to unwind 40 centimeters of the string. Okay. So a couple things showing. Again, we don't want to memorize anything really. Okay. So what do I got here, and how can I derive what I need? So we're looking for an angle. Okay. There's no time here involved. I do know that my total amount of string is 40 centimeters. That's the distance around the circle. So that's the one formula that we got to make sure we know is the circumference around the circle is equal to the amount of theta that you would turn times r. Okay. So we know r is 20 centimeters. Okay. And we don't know, well, we know that the total around the outside is actually 40. So 40 centimeters of the total circumference around that's going to move equals theta, which is the rotation, and r is 20. And they're both in centimeters here. I'd be really cautious against doing anything in on a non-unit, but non-standard unit of meters. But I think we're going to be okay here. So 40 divided by 20 would equal 2 radians. All right. So remember that 2 pi radians is 1 time around. So that's about 6 radians. Is 6.2 radians is 1 full rotation. So we're not going to even make it through 1 full rotations. You could change that over to degrees if you'd like, but angle is what they're looking for. I'm assuming radians will be good enough. Pretty standard radians. A golfer swings a 9-iron, a radius of 1.1 meters, with an average angular velocity of 5 radians per second. What's the tangential velocity of the club head? All right, so let's get back to what we got here. Okay, so what is tangential velocity? It's the actual distance traveled divided by time and around the outside. So in this case, I need to start with my distance. The distance, the circumference, is equal to radians times r. Okay, and I need to divide this distance divided by time. All right, so what do we know here? So I want the average angular velocity is 5. One last thing we can do here is know that these two things right here, change in angle per change in time, this is my angular velocity, times r equals my velocity tangential. When I divide by time, divide by time here, distance divided by time gives me my velocity tangential. Now I have my formula, it's just a plug and chug problem. This is going to be 5 times 1.1, and that's what, 5.5? 5.5, and we're going to be in unit of meters per second. Meters per second. Perfect. All right, next up, we have here a turntable is rotating at 33 1/3 rounds per minute. It's shut off. It slows down to a constant rate of coast to stop in 26 seconds. What's the angular acceleration? Okay, so we're going to talk about acceleration here as our topic for today here. So let's come back to that problem for us in a second. But what is angular velocity versus acceleration? Okay, so let's review again what angular velocity is. So angular velocity simply is the amount of change of angle per change in time. All right, so our unit on that would be, let's say, a radian per second. That would be your change in angle per change in time. And if you have a constant angular velocity, that means your wheel or your circle's changing at a pretty constant rate. So if you have a 33 and 1/3 rotations or revolutions per minute, then your angular acceleration is 0. Okay? Your angular acceleration, your change in angle per second would be 0. So we're going to use alpha, or this angular acceleration thing here, is your change in angular velocity. So that'll be the change in angular velocity per change in time. And this is really the same thing that we have for typical acceleration. So angular acceleration is just angular velocity, changing velocity, so angular velocity final minus angular velocity initial divided by the change in time. So at that point, the units would just be radians per time seconds squared. And this is our angular velocity. Okay. So with that being said, we can rearrange this formula to be angular velocity final equals, so I'm just going to um, pull this guy over, and we're going to get angular velocity initial plus a angular acceleration times time. So in this situation, this is one of our main linear relationships that's also with angular. It's a sloppy looking angle right there. So in this case, just one more quick thing before we try a problem on this is there a relationship between our linear formulas and our rotational movement here? I just showed you one of them. So these are pretty common formulas, which would be distance traveled. Sometimes we use an S here, or it could be an XT. I'm preferential to XT equals xi plus vit plus 1/2 at squared. At this point, you're getting pretty familiar with this. And our other formula would be vt equals vi plus at. And of course, we have velocity final squared equals velocity initial squared plus 2a, and then this would be the change in distance, change in physical distance. You could also do final minus initial here. Okay, so that means that there is an angular version of these. So the total distance location really is just your angle, okay? Your angle at time t. So where are you on your circle? Equals your angle initial at time 0. All right, initial and 0, same thing. Equals your angular plus angular velocity times time plus 1/2 times your angular acceleration times time. Kind of a common thing that people would typically do would be just subtract this guy over. If you subtract this guy over, you get the change in x. Your final position minus initial position equals your change in x. So you could have your change in angle equals angular velocity times time plus 1/2 angular acceleration times time. So this tells us the angle, the amount of actual angle that you went through. All right. The term for that is angular displacement, and that's a term you will see, angular displacement. Pretty common term. Now this one we just saw a second ago, which would be angular velocity final equals angular velocity initial plus angular acceleration times time. This one you could probably guess. It's going to be angular velocity final squared equals angular velocity initial squared plus 2 times angular acceleration. And then this is just the change in angle. Or it could be angle final minus angle initial. All right, so these are pretty useful formulas. Let's go ahead and let's try that problem that we saw a moment ago. The turntable is turning at 33 revolutions per minute. It's shut off, and it slows at a constant rate, coasts to a stop at 26 seconds. What's the angular acceleration? Okay, so a couple things we might want to do first is let's just convert this into, out of revolutions per minute, into something that's a little more convenient for us, which would be radians per second, and they're in seconds here. So let's do that quickly. 33.3 revolutions per 1 minute. Get rid of the minutes, and let's go and go to seconds. And then let's get rid of the revolutions, and go to radians. This is 1 to 60, and this is 1 revolution is 2 pi. So this is going to give us our radians per second. Alright, so 33.3 divided by 60 times 2 times pi. I'm getting 3.48 revolutions per second. Okay, 3.48, and that's my angular velocity in radians per second. Now this thing slows down in 26 seconds. Alright, so what's the angular acceleration? So at this point, just like in linear terms, I'm looking at my formulas. What formulas do I have? I don't want to memorize anything. Go to my laminated sheet, and I'll see I got angular velocity final equals angular velocity initial plus angular acceleration times time. And that's the formula that we're going to use. You can pause this and try it out here. So I'm coming to a stop. So this guy is 0. So in this case, 0 equals, I'm going to just rearrange this quickly here. So it's going to be, that's gone. So it's going to be minus angular velocity initial divided by the time equals the angular acceleration. Is that okay with that? Okay, so negative is the initial angular velocity, which is 3.48 divided by my my time, which is 26 seconds. This is going to give me a negative angular acceleration, meaning that I'm slowing down. I have a positive rotation with an oppositely direction of acceleration. Divided by 20 is negative 0.174. Negative 0.174. 174. That'd be radians per second squared. Alright, so that's a good example of using these formulas. And yeah. Alright, a ball radius 10 centimeters, so we're just going to be practicing some problems here, and it's going to range between angular velocity, angular displacement, and angular acceleration. So a ball has a centimeter of angular velocity of 2 radians per second, and angular acceleration of 0.5 radians per second. The ball rolls under the conditions for 5 seconds. What's the angular displacement and how far did the ball roll? Okay, so I'm going to just straight up grab my distance formula for circles. So it's going to be angular displacement, okay, equals, and I'm going to, well, it's angle at time t, angle at the initial 0 point, plus angular velocity times time, plus 1/2 angular acceleration times squared. I want to know, based on what they gave me, how much rotation am I making? So I subtract that over, I get my change in angle equals angular velocity, which is 2, and the time is 5 seconds, plus 1/2, and an angular acceleration of 0.5. So it's positive. So this is positive, and this is positive. So it looks like we're increasing the rate at which we're we're speeding up the rate of our rotation. So be careful on that. Are we slowing down or are we picking up? 0.5, and then it's going to be 5 squared. Okay, so let's do the math here. We got 25, which is 5 squared, times 0.5 times 0.5. That means this guy is 6.25. 6.25. That's the amount of angle we picked up due to the acceleration. This, of course, 2 divided by 5 is 10, and therefore this is just going to be 16.25. And that would be total angle rotated. That would be just a radian. Okay. Now we know that 6.25 radians is one time around. 6.2 radians is one time around. So we made 612, we made a little more than 2 revolutions. So how far the ball roll? Again, I'm going to go to my trusty distance formula. Circumference is equal to the angle that I went around times r. Okay, so my r, this is real important, you got to have that. Radius is 10. So I'm going to put this thing in divided by 100, that's 0.1 meters, times my angle I went through, 16.25, and I'm going to get 1.625 meters because I use meters. There we go. All right. This one. Let's do hypothesis. Student states that this record player slows down from normal speed to stop. Would this formula work out? Okay. And we've seen some like before. Angular velocity final equals angular velocity initial plus acceleration times time. This is 0. Subtract this over. Negative angular velocity initial divided by the time will give me my acceleration. So, yepers, that works. Okay. All right. So here we have a pretty significant question here, and there are a couple more of these come up here. So let's pause this video here, and we'll pick up on next video.